A king's arm once set the standard for an entire economy. This was the world of the lost metric systems of measurement that defined precision, a realm where forgotten rules built pyramids and powered global trade. By the end of this journey, you will understand how these ancient forms of accuracy still shape our modern world in surprising ways. Why did systems capable of such incredible engineering vanish almost completely? What hidden knowledge about precision disappeared with them? How much of our own technological confidence is built on foundations we no longer fully understand? What does it truly mean to measure something perfectly? That first farmer measuring a field with his own footsteps was doing more than just marking territory. He was inventing a language of trust. Without a shared understanding of length or volume, trade becomes guesswork, construction turns to chaos, and the concept of fairness evaporates. This was the genesis of measurement, a direct response to the most human of needs. It began with the body itself. The Egyptian cubit was the length of a pharaoh's forearm from elbow to fingertip. The Mesopotamian shekel was a specific weight of barley grains, a handbreadth, a foot, a pace. These were the original standards, portable and universally understandable. The historian Otto Neugebauer perfectly captured this, stating that the origin of metrology was found in the attempts to introduce order into the chaos of daily life. And this order was powerful. It allowed for the precise construction of pyramids that still stand today. It enabled the administration of sprawling empires, where taxes and tributes could be calculated fairly across vast distances. It formed the backbone of the world's first legal codes, which specified fines and payments in exact measures of silver or grain. This was not just about practicality. It was humanity's first conscious effort to impose a mathematical framework onto the unpredictable world, a quest for precision that would fuel progress for thousands of years. But how do you move from a king's arm to the perfection of the Great Pyramid? How does a simple concept become a tool capable of shaping stone into immortal geometry? The answer lies in a crucial and often forgotten leap in thinking. The moment these personal measures were refined into something far more sophisticated and enduring. That carved rod of black granite was more than just a tool. It was the very embodiment of order. In the hands of an Egyptian architect, this royal cubit translated divine will into architectural reality, setting the precise dimensions for a pharaoh's journey into the afterlife. This unit of measure, roughly 52.5 centimeters long, was a masterpiece of subdivision. It was split into 7 palms, and each palm was further divided into 4 digits. This gave the Egyptians a system of 28 smaller units, a level of granularity that allowed for breathtaking accuracy in their designs. But this precision was not distributed equally across society. A royal cubit used for state monuments and temples was actually slightly longer than the common cubit used in everyday markets and homes. This was measurement as a statement of power, a physical reminder that the state operated on a grander, more exacting scale than the common people. The Greek historian Herodotus observed this system in action and wrote that the Egyptians achieved a level of architectural accuracy and beauty that was simply unmatched anywhere else in the ancient world. We can see this in the Great Pyramid of Giza. The sides of its square base are virtually identical in length, varying by less than 0.05%. To put that in perspective, building a structure that precise today at that scale would be a formidable challenge even without our laser-guided tools. The integrity of this entire system, however, rested on a fragile foundation, a physical object. The master cubit, a rod carved from durable stone like granite, was kept secure in a major temple. This meant the definition of length was a spiritual and political concern, literally held in the hands of the priesthood and the pharaoh. So what happened when a fire damaged that temple, or a new dynasty came to power and introduced a new standard? What happened when the physical ruler itself was lost, or worse, deliberately corrupted? This was the system's greatest vulnerability, a flaw that other civilizations would desperately try to solve. While the Egyptians carved precision in stone for the gods, the Mesopotamians hammered it into metal for the marketplace. In the sun-baked courtyards of ancient Babylon, the true measure of a society was not found in towering monuments, but in the careful balance of a merchant's scale. Here, the shekel was king. This was not a unit of length, but of weight, and it was born from the most fundamental commodity of all, grain. A single shekel was defined as the weight of approximately 180 grains of barley, a direct link to the agricultural reality that fed the empire. This simple, tangible standard became the bedrock of an astonishingly sophisticated economic machine. Merchants and traders relied on sets of stone weights, often beautifully carved in the shape of ducks or lions and inscribed with cuneiform markings. These were used to weigh out silver, the common currency, and barley itself, the lifeblood of the economy. The entire system was built on a base 60, or sexagesimal, framework. 60 shekels made 1 mina, and 60 minas made one much larger unit called a talent. This mathematical choice was a stroke of genius. The number 60 is divisible by 1, 2, 3, 4, 5, 6, 10, 12, 15, 20, and 30. This made calculating fractions and dividing goods for trade or tax collection incredibly straightforward, far easier than dealing with the more limited divisors of a base 10 system. It is this very same Mesopotamian logic that echoes in our modern world every time we check a clock, 60 minutes in an hour, or use a protractor, 360 degrees in a circle. The importance of this precision was a matter of law, not just convenience. The Code of Hammurabi, one of the world's oldest and most complete legal codes, spelled out severe penalties for any merchant caught using false weights or measures. The law was explicit, designed to protect the poor from the powerful, and to ensure that trust was not a luxury but a guarantee in every transaction. This was measurement as the guardian of social order, a tool to prevent chaos and enforce fairness across a vast and diverse empire. Archaeological discoveries bring this system to life. Exquisitely carved duck weights certified by royal authorities have been found from the city of to the farthest trading outposts. They were more than tools, they were symbols of a certified, reliable standard that enabled long-distance trade across the known world. A merchant in Babylon could strike a deal with a trader from hundreds of miles away, confident that a mina of silver weighed there was the same mina of silver weighed here. This created an early form of economic globalization, all built upon a shared, precise understanding of value. But how did a system so perfectly designed for weighing grain and silver translate to the demands of building ziggurats or mapping the stars? The answer was hidden in the system's own elegant mathematical soul. A Roman legionary did not just march, he measured. With every fifth step, he marked a single passus, a pace exactly 5 Roman feet in length. This repetitive action was the engine of imperial expansion, transforming unknown landscapes into orderly spaces of Roman control. When a legion halted for the night, this same unit of measure allowed them to lay out a perfect rectangular fortress, complete with defensive walls, commander's tent, and orderly rows for the soldiers, all in a matter of hours. This was the power of the Roman foot or pes, a unit of approximately 29.6 centimeters that became the heartbeat of an empire. Its consistency was a matter of state power. Across the empire, from the Forum in Rome to the bustling markets of Londinium and Antioch, official standards were carved in bronze or marble and set into public walls. Every merchant, every tax collector, every engineer could come and verify their own measures against this immutable stone, ensuring that a foot in Gaul was the same as a foot in Egypt. The architect Vitruvius detailed in his seminal work, De Architectura, how this system was essential for the empire's greatest achievements: aqueducts, those miracles of engineering that brought fresh water to cities, relied on the pest to calculate the precise, gentle gradients needed for water to flow for miles. Entire new cities were planned with a grid of streets measured out in these standard units, imposing a uniform, rational order on the landscape. This was more than just engineering. It was a powerful tool of Romanization. To adopt the Roman foot was to accept Roman logic, Roman administration, and Roman control. The ultimate expression of this was the Roman mile, 1,000 paces, which became the standard for measuring the empire's vast and legendary road network. These roads, marked with milestones, were the arteries of communication and commerce, binding the empire together with a single, measurable thread. Yet this magnificent uniformity was incredibly fragile. When the central authority of Rome crumbled, the system it enforced began to splinter. The carefully maintained standards in the forums were neglected, damaged, or forgotten. In the absence of a central power, what was once a universal foot began to shrink and grow, varying from one valley to the next. The fall of Rome did not just topple a government. It shattered the very tools of measurement that had held an empire together, plunging Europe into a long age where no two places could agree on the length of a simple foot. While the Romans imposed order through military might, Imperial China sought a different kind of precision, one that resonated with the harmony of the cosmos itself. In the hands of a Han Dynasty master builder, an intricately carved ivory ruler was not just a tool for measurement, but an instrument for aligning human creation with the fundamental principles of the universe. The primary unit, the chi, was more than a length of about 23 centimeters. It was a building block of cosmic order. This Chinese foot was part of an elegantly simple decimal system, where 10 chi made 1 zhang. This logical structure was deeply woven into the fabric of Chinese statecraft and philosophy. Ancient texts recount how the legendary Yellow Emperor himself standardized measurements to bring order to his realm, firmly linking good governance with metrological consistency. This was precision with a purpose far beyond engineering. It was about maintaining balance between heaven, earth, and humanity. The profound connection between measurement and the cosmos is detailed in texts like the Zhu Bai Suan Jing, a classic mathematical work that explains how these same units were used for astronomical calculations and creating the imperial calendar. The length of a shadow cast by a standard gnomon, measured precisely in chi, could determine the solstices and guide agricultural cycles for the entire empire. On the ground, the bu, a double step of 5 chi, became the standard for surveying land. This created a rational and repeatable system for agricultural planning and taxation, the very engine that powered the imperial bureaucracy for centuries. The commitment to this unified standard was absolute. After the turmoil of the Warring States period, the first emperor of the Qin dynasty had standard measures cast in bronze and distributed to every corner of his new, unified empire. These artifacts were not mere suggestions. They were the law, physical embodiments of a central authority determined to erase local variations and administer a single, coherent state. This drive for a unified standard from a central power foreshadowed a challenge that would later confront the entire world. Yet, such a sophisticated system evolved in remarkable isolation from the measurement traditions of the West. Its development was shaped entirely by a unique philosophical and political context, one that saw measurement not as a tool of conquest, but as a thread in the sacred tapestry of the cosmos. In the quiet of an observatory during the Gupta Empire, a scholar's own finger became a tool for mapping the heavens. The angular, a finger's breadth of roughly 1.9 centimeters, was the fundamental unit of a system that scaled from the human body to the cosmos itself. 24 of these finger widths made one hasta, a cubit, and 4 hastas made one danus, the length of a bow. This was measurement rooted in the human form, yet it reached for the stars. With these units, astronomers calculated the staggering distances to the planets, while temple architects laid out sacred spaces whose every dimension resonated with spiritual and mathematical harmony. This was a world where the microcosm of the body and the macrocosm of the universe were intimately linked by a single, scalable standard. The state understood this precision was not merely philosophical, it was the bedrock of economic trust. The ancient treatise on statecraft, the Arthashastra, laid down severe penalties for anyone caught using false weights or measures. In the bustling markets of Pataliputra, the integrity of the hasta and the weight of a coin were protected by law, ensuring fairness in a complex and sprawling economy. But the most stunning applications of this system were found in the realm of sacred geometry. The Vedic texts known as the Sulba Sutras provided detailed instructions for constructing elaborate fire altars using these very units. The task was not just about building a structure, it was a ritual act of creation. The texts demanded, for example, an altar with an area exactly equal to that of another, more complex shape. To achieve this, the builders, using their measures of angulars and hastas, had to possess a sophisticated, practical understanding of geometry, including the Pythagorean theorem, centuries before it was formalized in the West. They were solving advanced geometric puzzles with a rope and a ruler, all to satisfy divine specifications. This system was not perfectly rigid, it breathed and adapted. Different regions and craft guilds sometimes used their own slight variations, yet a core set of principles provided a surprising coherence across the vast subcontinent. This flexibility within a shared framework hints at a deeper philosophical truth. The seamless movement from a finger's width to a bow's length to the orbit of a planet was possible because of a holistic worldview that saw no strict separation between the human, the divine, and the cosmic. The same principles that govern the proportions of a temple were believed to govern the motion of the heavens. So when an early Indian astronomer used these body-based units to make a bold attempt at calculating the circumference of the Earth, it was not a leap of faith, but a logical extension of a system where the individual was a perfect reflection of the universe. How did other cultures, building in isolation, confront this same fundamental challenge of creating a perfect, unchangeable standard? The Mayan priest-astronomer saw a universe woven from numbers where time and space were a single, unified fabric. High atop the pyramid at Chichen Itza, he would track the journey of Venus not just as an event, but as a measurement, his calculations governed by a base 20 or vigesimal system. This framework created one of history's most intricate and beautiful metrologies, one where the units of the land and the cycles of the heavens were inseparable. The Hunab, a unit for measuring fields and property, existed in perfect harmony with the Kayin, the single day, and the Winal, a period of 20 days. Their famous long count calendar did not just track years, it could pinpoint a date across a span of millions of years, revealing a desire for precision that was almost cosmic in its ambition. This was not precision for commerce or construction alone. It was precision for aligning human life with the perceived rhythms of the gods. The very stones of their cities were laid to this celestial score. Temples and entire urban plans were oriented to capture the sun's light on the equinoxes or to frame the rising of certain stars. Their architecture was not simply built in space. It was a physical manifestation of their timekeeping, a permanent clock built from limestone and shadow. This system's foundation was radically different from those in the Old World. The standard was not a pharaoh's arm or a basket of barley. The ultimate reference point was the sky itself, the observed, repeating cycles of the sun, the moon, and the planets. This astronomically derived precision granted them an incredible predictive power. They could forecast eclipses and model the complex motions of Venus with an accuracy that would not be matched in Europe for over 1,000 years. This knowledge was the core of their religious and cultural identity, a sacred science that dictated the timing of rituals, the legitimacy of kings, and the fate of their world. Then their civilization faced a profound decline. The great ceremonial centers were abandoned, and the deep, nuanced understanding behind this magnificent system faded into the jungle, leaving modern scholars to decipher its logic from the silent testimony of stone stelae and a handful of surviving bark paper codices. How could a society that never used the wheel or metal tools achieve such a staggering command of mathematics and astronomy? Their legacy forces us to reconsider the very definition of technological sophistication, proving that the most advanced tool a civilization can possess is not made of iron, but of pure, unyielding intellect. A merchant from Florence holds up a length of fine cloth, insisting it measures a full L. His customer from London scoffs, pulling out his own measuring stick to prove the Florentine L is a full 2 inches shorter. In the bustling market square of a medieval European town, this was not a simple disagreement, it was a daily reality. The collapse of Rome had shattered the universal language of the pes, the Roman foot, plunging the continent into a metrological tower of Babel. What was called a foot in one German principality could be several inches different from the foot used just across the river. A pound of wool weighed in Paris was not the same as a pound weighed in Toulouse. This was more than mere confusion. It was a system of controlled chaos that served the powerful. Local lords and trade guilds guarded their unique standards jealously, often manipulating them to tax more effectively or to grant unfair advantages to their own members. The great French thinker Voltaire later captured the absurdity of the age by noting that the Holy Roman Empire was neither holy nor Roman nor an empire. One could easily add that its measurement systems were a perfect reflection of that political incoherence. This fragmentation strangled economic growth. An inventor in Milan could write down the precise dimensions for a revolutionary new water pump, but an engineer in Flanders would have no way to accurately reproduce it without knowing the exact local variation of the Milanese foot. The true scale of this complexity is frozen in time within documents like the Domesday Book, a vast survey of 11th century England that recorded land holdings using a dizzying patchwork of local units like virgates and hides, whose values shifted from one village to the next. This was a world drowning in its own contradictory rules, a world that was crying out for a single, rational solution. That solution would not come from a king or an emperor, but from the revolutionary thinkers of the Enlightenment, who saw in this metrological chaos a problem that reason alone could finally solve. Inside Galileo's workshop, the erratic swing of a pendulum was not just a curiosity, it was a call to arms. The scientific revolution demanded a new language of precision, one that could be replicated in London, Florence, or Prague. This was a shift from simply observing the world to quantifying it, and the old, chaotic systems of measurement were now a direct obstacle to progress. A scientist like Newton could not simply describe the force of gravity. He needed to measure it with numbers that meant the same thing to every other natural philosopher. This intellectual ferment gave rise to a radical new idea, a measurement system rooted not in a king's arm or a basket of grain, but in the immutable laws of nature itself. The English philosopher John Wilkins, a founding member of the Royal Society, gave this dream its first concrete form in 1668. He proposed a decimal system where the fundamental unit of length would be defined by a pendulum that swung exactly once per second. Imagine the elegance of that concept, a meter born from the steady, predictable rhythm of a clock, a standard literally drawn from the physics of the planet. This was more than a scientific proposal. It was a philosophical declaration that human knowledge should be built on a foundation accessible to all of humanity, not locked away in local customs. The quest for a universal measure became inextricably linked with the Enlightenment's core ideals of reason, progress, and international cooperation. How could such a beautifully simple and idealistic proposal be forged into a practical, working system for the entire world? The answer would not emerge from a quiet academic society, but from the fiery political crucible of a nation completely reinventing itself from the ground up. The old world of kings and cubits was to be swept away in a single, decisive stroke. In the fervor of the French Revolution, the very fabric of reality was being rewoven, and that included the tangled threads of measurement. The new republic tasked its greatest scientific minds with an audacious goal: to create a system of measurement for all time, for all people. This was not to be based on any monarch's limb or any local custom. It would be drawn from the earth itself, a grand gesture of human reason. The meter was defined as 1/10,000,000th of the distance from the North Pole to the equator, along the meridian passing through Paris. This was more than science, it was a philosophical revolution, severing measurement from arbitrary authority and grounding it in the permanence of the planet. To turn this vision into reality, two astronomers, Jean-Baptiste Delambre and Pierre Méchain, embarked on a legendary 7-year expedition. Their mission was to triangulate the arc of the meridian with unprecedented accuracy, a task that plunged them into a landscape torn by war, suspicion, and hardship. They faced imprisonment, hostile mobs who mistook their strange instruments for tools of witchcraft, and the immense physical challenge of hauling delicate equipment across mountains and through treacherous terrain. Their dedication, however, resulted in a physical object of pure authority, the Meter des Archives, a pristine bar of platinum that became the tangible definition of the meter in 1799. This new system was a masterpiece of logical design. It was decimal, meaning everything was based on the number 10, making calculations dramatically simpler than with the old base 60 or base 12 systems. The units were coherently linked. The gram was defined as the mass of 1 cubic centimeter of water, creating a perfect bridge between length, volume, and mass. To sell this radical change to the public, the revolutionary government launched one of history's first major propaganda campaigns. They sent out metric missionaries to towns and villages, armed with pamphlets and new decimal clocks, trying to convince a skeptical populace that the familiar awn for cloth and the boiseau for grain were relics of a tyrannical past. Yet the resistance was fierce. The old measures were not just tools, they were the rhythm of daily life, deeply embedded in language, song, and memory. A farmer knew what a journey, the amount of land one man could plow in a day, felt like in his bones. The abstract perfection of the hectare was a cold and distant concept. This clash revealed the enormous gulf between a top-down imposition of rational order and the stubborn, lived reality of human tradition, a conflict that would define the metric system's difficult journey to global dominance. Locked away in a vault near Paris, a small, polished cylinder of platinum and iridium held the weight of the world. This was the international prototype kilogram, the physical object that defined mass for over a century. Here was the paradox of the metric system laid bare. While the meter had been liberated, tied to the speed of light, the kilogram remained a prisoner of the physical world, a man-made artifact. Known as the kilogram des archives, this single, shining cylinder was the ultimate standard. Its stability was so critical it was almost never touched, kept under 3 glass bell jars to protect it from the tiniest speck of dust. Yet, despite this obsessive care, the artifact was vulnerable. Every time it was carefully cleaned and weighed against its official copies, scientists detected a disconcerting drift. The masses were changing minutely relative to each other. The fundamental unit of mass was itself unstable. This tiny, inconsistent wobble at the heart of precision launched a scientific quest lasting more than a century. The goal was audacious: to redefine the kilogram not by a physical object, but by a fundamental and unchanging constant of nature. This pursuit pushed experimental physics to its absolute limits. Scientists developed an incredible device called a Kibble balance, which measures mass by balancing it against an electromagnetic force. This intricate process effectively linked the kilogram to Planck's constant, a fundamental value from quantum mechanics. The kilogram was no longer a thing you could hold, but a fixed number of quantum energy packets. In 2019, this century-long dream was finally realized. The kilogram, along with all other base units of the international system, was officially redefined in terms of universal constants. The journey from a grain of barley to a fundamental quantum value represents the ultimate refinement of precision, a system now built on the bedrock of the universe itself. Yet, as this scientific revolution was unfolding, a very different struggle for standardization was taking place across the English Channel. A sailor heaving a lead line into the dark water was not just checking the depth, he was using his own body to navigate the globe. The fathom, measured by the span of his outstretched arms, gave him the information he needed to avoid running aground. This was the essence of the British imperial system, a world of measurement built not from a grand philosophical blueprint, but from the raw, practical needs of daily life over centuries. It was a patchwork of Roman, Anglo-Saxon, and medieval units slowly woven together and given the force of law by acts of parliament. The foot, the pound, and the gallon became legally defined, yet their origins remained stubbornly human and agricultural. A foot was still roughly the length of a man's foot, a gallon was a volume for grain or wine, and an acre was the amount of land a team of oxen could realistically plow in a single day. This was a system born from the soil and the sea, not the study. The British Weights and Measures Act of 1824 represented the most ambitious attempt to take this historical jumble and forge it into a single, coherent standard for the entire empire. It was a monumental effort at consolidation, creating a unified, if incredibly complex, framework for global trade and colonial administration. The system's spread was a direct function of British power. It traveled on merchant ships and with colonial administrators, becoming deeply entrenched in the United States and other territories. This created a powerful bloc of nations that, even after gaining independence, held onto the familiar units of feet and pounds. This persistence, especially in America, is a masterclass in cultural and economic inertia. The cost of changing an entire nation's infrastructure, from every road sign and factory blueprint to every cookbook and weather report, is almost unimaginably vast. It is a testament to the fact that a system does not need to be perfectly logical to be deeply embedded. The ongoing global standoff between metric and imperial is a clear reminder that the story of measurement is not just one of scientific progress, but a continuous negotiation between cold rationality and the warm, stubborn weight of human habit. So why would a modern, technologically advanced nation choose to remain with a system based on the length of a king's thumb or the plowing capacity of an ox? The forces at work are far more powerful than simple tradition. The true chaos of ancient markets was not in the crowded streets, but in the hollow spaces inside their containers. Step into the hold of a Phoenician merchant ship, rocking gently on the Mediterranean waves. Your fortune rests on the cargo of wine and olive oil, each carefully sealed inside a distinct ceramic jar called an amphora. But these were not just pots, they were the original units of volume. Different city-states produced amphorae with slightly different capacities, and a trader had to know these variations by heart. A deal struck using the amphorae of Carthage could mean a significantly different profit than one using the jars from Athens. This was a system built entirely on the shape of a clay vessel, a standard that was literally baked into its form. This reliance on physical containers created a history of volume measurement far messier than that for length or weight. A unit like the Roman amphora was first a specific jar, then it became an abstract measure of capacity. The medieval tun was simply a large wooden cask for wine, and the English gallon started its life as a common pot for ale or wine before anyone wrote its definition down. The potential for confusion was enormous. In England, an ale gallon was not the same as a wine gallon. The ale gallon was larger, a distinction born from the different trades, taxes, and guilds that govern the production and sale of these two essential beverages. This was not an accident, it was a feature of a system where measurement was tailored to the product being measured and the tax being collected. The financial stakes were immense. Runners derived a huge portion of their revenue from duties on measured volumes of staple goods. A tax on a ton of wine, a bushel of grain, or a hogshead of salt was the lifeblood of treasuries. This made the standardization of volume a pressing matter of state security. To prevent fraud and ensure a fair, or at least consistent, collection of taxes, authorities began creating official standard measures. These were master containers, meticulously crafted from durable materials like brass or copper, and they were kept under lock and key in the town hall. Once a week, perhaps on market day, local merchants would bring their own wooden or earthenware vessels to be checked against this official standard. Any container that did not match was confiscated or destroyed. You can still see these beautiful, worn brass standards in museums today, tangible proof of the eternal struggle between buyer and seller, citizen and state. The legacy of this container-based thinking is written into the modern world in surprising ways. The American liquid gallon, for instance, is defined as 231 cubic inches. This seemingly random number makes perfect sense only when you know its history. It is a direct descendant of the English wine gallon, a unit that was not conceived mathematically but physically. It was based on the volume of a cylindrical vessel 8 inches in diameter and 6 inches deep. The space inside that specific historical bucket became the definition of a gallon for a new nation. The centuries-long struggle to define something as simple as a gallon reveals how deeply measurement is entangled with economics, politics, and the most basic routines of daily life. How did humanity finally break free from this world of arbitrary pots and casks? The leap to a system where a liter is definitively a cubic decimeter required a complete rethinking of the very relationship between length, volume, and the physical world. 17 nations gathered in a Paris conference room in 1875 to sign a document that would quietly reshape the world. The Treaty of the Meter was not a peace accord, but it was a profound agreement to end a different kind of conflict, the chaos of incompatible measurement. This was the moment the metric system shed its revolutionary French skin and was reborn as a global project. It established the International Bureau of Weights and Measures, a permanent institution dedicated to guarding the sacred prototypes of the meter and the kilogram, and to propagating the system across the globe. The driving force was no longer just philosophical idealism, but the relentless, practical engine of industry. As nations rapidly industrialized, they faced a new problem. German machine parts had to fit with French locomotives. Japanese electrical components needed to match American specifications. The metric system, with its decimal simplicity and its coherent design where a cubic decimeter of water was both a liter in volume and a kilogram in mass, was the perfect language for this new era of technology transfer and global supply chains. It was a tool for modernization. Nations like Germany and Japan adopted it not out of political allegiance, but as a strategic move to streamline their economies and compete on the world stage. The system spread through the silent authority of scientific journals and technical textbooks, becoming the default language of engineering and physics. Yet this conquest was not swift or universal. Resistance was deeply entrenched. The United Kingdom, with its vast empire built on inches and pounds, held out for nearly a century, only beginning a formal, and often fiercely resisted, metrication process in 1965. The final codification of this global standard came in 1960 with the creation of the International System of Units, known as C. This was the metric system fully matured, now incorporating units for electricity, temperature, and light, creating a single, unified framework capable of describing the entire physical universe. This triumph of global uniformity, however, had a shadow. It required the deliberate erasure of hundreds of local and traditional systems. The Scottish ell, the Portuguese moio, the countless regional acres and bushels that had structured daily life for generations, all were swept aside. These were not just units, they were repositories of local knowledge, their sizes and names reflecting specific landscapes, agricultural practices, and social structures. The victory of the meter was a victory of efficiency over idiosyncrasy, of the global over the local. What unique wisdom about the land or about community was lost when we traded the rhythms of a local field for the perfect, silent geometry of a hectare? This trade-off between seamless global communication and rich cultural heritage is the complicated and often unspoken legacy of the metric century. A sea captain in the middle of the ocean was navigating blind. Without a way to know his exact longitude, every voyage was a gamble with shipwreck. The solution was not a better map, but a better clock. If a captain could carry the precise time from his home port, he could compare it to the local solar time and calculate his position. The problem was that no clock of the era could survive the pitch and roll of a ship, or keep accurate time across months of salt air and temperature changes. This was not just a scientific challenge, it was an economic and strategic one, so critical that the British Parliament offered a prize of £20,000, a fortune, to anyone who could solve it. This quest for perfect time forced a revolution in measurement itself. For most of human history, time was a celestial phenomenon. Read from the moving shadow on a sundial or the steady drip of water in a clepsydra. The pendulum clock, invented by Christian Huygens in 1656, changed everything. By harnessing the regular, repeating swing of a weight, it brought a new order of precision to the day, slicing time into seconds with a consistency that mechanical clocks had never before achieved. This accuracy was the key that unlocked new scientific discoveries, allowing thinkers like Isaac Newton to formulate laws of motion that depended on precise intervals. Yet, even the finest pendulum clock was useless on a storm-tossed ship. The solution came from a self-taught English carpenter and clockmaker named John Harrison. He dedicated his life to building a series of marine chronometers, intricate masterpieces of brass and wood that used innovative mechanisms to counteract the motions of the sea. His fourth and final chronometer, known as H4, was no larger than a pocket watch. and on a trial voyage to Jamaica, it lost only 5 seconds over the entire 147-day journey. Harrison had effectively shrunk the stability of an observatory clock into a portable box, finally conquering the longitude problem. This achievement demonstrated that precision was not just an abstract goal, but a tool of immense tangible power, capable of saving lives, protecting fortunes, and expanding empires. The definition of the second itself began to shift. It was no longer good enough to define it as 1/86,400th of a day, because the Earth's rotation is imperfect and gradually slowing. Scientists moved to a definition based on the Earth's orbit around the Sun, but even that was not stable enough for the new atomic age. In 1967, the second was fundamentally redefined. It became the duration of 9,192,631,770 periods of the radiation, corresponding to the transition between 2 hyperfine levels of the ground state of the cesium-133 atom. Time was no longer tied to the motion of planets, but to the immutable, universal vibration of an atom. This made time the most precisely measurable physical quantity, a staggering achievement that forms the silent, invisible bedrock for our modern world. The entire global positioning system, for instance, is a network of atomic clocks in orbit. For GPS to pinpoint your location on the ground, those satellite clocks must be synchronized to within nanoseconds. A timing error of just 1/1000th of a second would translate into a positioning error of nearly 1 foot. This relentless drive for perfect time has forced a re-evaluation of all other measurement. The meter is no longer a metal bar in a vault. It is now defined as the distance light travels in a vacuum in 1/299,792,458 of a second. The kilogram was liberated from its platinum cylinder by being tied to Planck's constant, a value measured using the impeccable regularity of atomic clocks. In our modern C system, the second is the golden thread that weaves through the entire tapestry of measurement, connecting length, mass, and electricity through the fundamental constants of physics. The journey from a sundial's shadow to the quantum vibration of an atom represents the ultimate abstraction of precision, a system completely divorced from human perception, yet one that now defines the very fabric of our technological reality. We still measure our world with the ghosts of forgotten rulers. Listen closely to the words we use every day, and you will hear the echoes of ancient markets and royal decrees. When we warn someone not to give an inch, we are invoking the precise, subdivided foot of a Roman surveyor. To rule with an iron rod is to govern with the unyielding authority of a master standard, a physical bar against which all others are judged. These phrases are not just metaphors, they are linguistic fossils, preserving the memory of systems that have long since vanished from practical use. The very word mile comes directly from the Latin milia passuum, meaning 1,000 paces, a direct auditory link to the rhythmic stride of a legionary marking his conquests. Our language is a living museum of this metrological history. The term assay, meaning to test the purity of a metal, was born in the bustling markets of Mesopotamia and medieval Europe, where a merchant would precisely weigh a sample of silver or gold against certified stone weights. Even the humble word ton carries the weight of history, a relic of the large wine cask called a ton that was once a standard unit of volume in transatlantic trade. This container, so vital to commerce, gave its name to a measure of mass, forever linking the space inside a wooden barrel to the weight of the goods it could carry. Some phrases are more recent, yet just as revealing. The mysterious origin of the whole 9 yards is widely believed to refer to the length of the standard ammunition belt in a World War II aircraft gun. When a pilot had given his target the whole 9 yards, he had fired every last bullet from a belt measured out by the yardstick of industrial warfare. These are not abstract units in a textbook. They are measurements tied to life, death, work, and trade. They remind us that our ancestors lived in a world where measurement was a tangible, sensory experience. You felt the weight of a pound in your hand. You saw the length of a fathom in your outstretched arms. You knew the volume of a bushel from the basket you carried from the field. This was a world you scaled to the human body and its labors, a stark contrast to our modern reality of invisible atomic vibrations and the speed of light. The stubborn persistence of these terms, long after the systems they refer to have been abandoned, is a powerful testament to the deep cultural imprint of measurement. It proves that these systems were not just tools for building and trading, but the very grammar of daily life and social interaction. Every time we use these phrases without a second thought, we are speaking in a forgotten language of precision, one that still measures our past. An ancient map is a beautiful lie, its coastlines and kingdoms sketched across a grid of forgotten numbers. Unfold Ptolemy's Geographia, and you will find a world measured in stadia, a Greek unit that was the length of a stadium track. The problem was, a stadium in Athens was not the same as a stadium in Alexandria. This was a world without a common language of distance, where every mapmaker's ruler was subtly different, making precise scaling and navigation a near impossibility. The dream of accurate cartography was entirely dependent on the standardization of measurement. A map is a promise that 1 inch on paper equals 1,000 paces on the ground, but that promise is meaningless if no 2 cities agree on the length of a pace. This confusion had profound consequences. Christopher Columbus's famous miscalculation, his belief that he had reached the Indies, stemmed directly from this meteorological chaos. He relied on an estimate of the Earth's circumference that used the Arabic mile, but then interpreted it using the shorter Roman mile. The world, in his calculations, shrank, leading him to vastly underestimate the vast ocean that lay between Europe and Asia. The greatest puzzle, however, was longitude. Determining how far east or west a ship had traveled was a problem of precise timekeeping. If a captain knew the exact time at his home port and could compare it to the local solar time, the difference would reveal his longitude. But no clock could survive the violent motions of a ship and keep accurate time across a months-long voyage. The solution, found in the 18th century with John Harrison's marine chronometer, was as much a cartographic revolution as a horological one. It provided the final piece of data needed to fix a ship's position accurately on a blank chart. The French project to define the meter was itself one of history's most ambitious maps. The astronomers D'Alembert and Mécain were not just measuring the Earth, they were literally triangulating its curvature, creating a precise geodetic survey across hundreds of miles of French countryside to extract a single, perfect number from the planet's arc. This new, universal unit finally allowed for the creation of maps that could be seamlessly connected across national borders. The 1-to-1 million International Map of the World project, begun in 1913, was a testament to this new global scale, a collaborative effort to map the entire planet with a single, consistent metric. Yet the old systems never fully vanished. The nautical mile, a unit still vital to pilots and sailors, is a direct descendant of the Mesopotamian sexagesimal system. It is defined as 1 minute, 1/60th of a degree of latitude. This direct link to the geometry of the Earth itself is a living fossil of an ancient way of measuring. The slow triumph of standardized measurement over local variation did more than just produce better maps. It fundamentally altered humanity's perception of its home. The planet was no longer a collection of disparate, vaguely known lands, but a single, measurable entity. It enabled a global consciousness, the profound understanding that we all live on one interconnected sphere, a concept made real only when we could finally agree on how to measure it. A land dispute in a medieval English court hinged not on a written deed, but on the memory of an elder who recalled the exact length of the local perch used to mark the boundary a generation ago. His testimony was the only remaining link to a standard that had since vanished, leaving justice dependent on fragile human recollection. This scene reveals a profound truth. Standardized measurement has always been a cornerstone of legal justice, an objective foundation for resolving disputes over property, trade, and taxation. Ancient legal codes understood this principle intimately. The Code of Hammurabi specified severe penalties for merchants using false weights, while the Magna Carta explicitly demanded 1 measure of wine throughout the realm and 1 measure of corn. These were not minor clauses, they were acknowledgments that metrological fraud was a direct form of oppression. In a world without standardization, the powerful held a distinct advantage. A local lord could subtly alter the size of the bushel used to collect his grain tithes, or redefine the acre when surveying peasant lands, effectively increasing his own wealth while leaving his tenants with no objective way to appeal. This manipulation of measurement was a silent, pervasive tax on the powerless. The push for the metric system during the French Revolution was, at its heart, a radical political statement. It aimed to create a system that was precisely the same for the peasant and the aristocrat, a tool of equality designed to shatter a key instrument of feudal control. This philosophical link between measurement and fairness endures in our modern era. Consumer protection laws in nearly every country universally mandate the use of certified and accurate scales and fuel pumps in commerce. When you buy a pound of coffee or a liter of gasoline, you are protected by a legal and metrological framework that is the direct legacy of this century's long struggle against fraud. The very concept of a standard is inherently legal. It is a rule against which compliance is judged, making the science of measurement, metrology, a fundamental, if invisible, pillar of the rule of law itself. Yet this triumph of universal standards came with a cost. The loss of local units like that medieval perch also meant a loss of local autonomy and the traditional knowledge embedded in those communities' specific measures. A unit like the Scottish acre varied with the quality of the land, its size reflecting local agricultural reality rather than an abstract geometric ideal. The history of measurement is therefore not merely a technical progression. It is a deeply social and political narrative, a continuous struggle for justice and equity. And this leaves us with a question that resonates powerfully in our globalized world. How do we balance the undeniable need for universal standards with a respectful acknowledgement of the local practices and knowledge they inevitably replace? The perfect proportions of the Parthenon were not an artistic accident, but a mathematical mandate. Greek architects designed this iconic temple using a specific module, the Doric foot, to govern the relationship between every single element. The space between the columns, the height of the steps, the curve of the stylobate, all were determined by this single unit of measure. This was not merely a practical tool for construction. It was a philosophical pursuit of ideal beauty, an attempt to translate harmonic ratios from music and geometry into stone. They believed these specific proportions, often related to the golden ratio, resonated with a universal order, creating a structure that was not just seen but felt. This sacred geometry became the hidden code for Western architecture for centuries. A medieval master mason, entrusted with building a cathedral, would have possessed his own sacred standard, perhaps an iron rod representing the local foot. He used this rod not just to ensure walls were straight, but to encode the building with spiritual significance. The three-part division of a Gothic cathedral's facade often reflected the Holy Trinity, while the overall floor plan in the shape of a cross was a measurement made manifest of faith. These architects were working within a symbolic universe where every dimension carried a layer of meaning invisible to the untrained eye. The system they used, the Byzantine cubit or the Romanesque perch, was as much a part of the design as the stained glass or the sculpted gargoyle. This knowledge was often guarded, passed down through guilds as a form of esoteric power. The specific reasons why one module was chosen over another, or why certain ratios were considered more divine, have been partially lost, leaving art historians to piece together the clues from ancient manuscripts and the buildings themselves. In the East, this connection was even more explicit. The construction of a Hindu temple was governed by the Vastu Purusha mandala, a complex geometric diagram that specified every measurement based on cosmic principles and the story of a celestial being pinned to the earth. The temple was not a building, it was a map of the cosmos, and its measurements were the key to aligning the human and divine realms. The modern shift to the metric system fundamentally changed this relationship. A meter is a meter, a clean, abstract decimal. It carries no inherent symbolic weight, no connection to a king's arm or the harmonics of the universe. This has allowed for incredible feats of engineering and global collaboration, but it has also largely stripped the act of measurement of its philosophical and spiritual dimensions. When an architect today designs a building, they are almost certainly thinking in meters and centimeters, calculating for function, cost, and efficiency. The questions are how much space is needed and what is the most economical way to enclose it, not what cosmic truth can be expressed through the ratio of width to height. We have gained global consistency and scientific precision, but we have lost the hidden language that once turned buildings into prayers and stone into song. The silent, uniform spaces of our modern cities stand as a testament to this trade-off, challenging us to wonder what layers of meaning we have willingly left behind in our quest for perfect, universal measure. That aisle of wrenches and lumber is a monument not to efficiency but to memory. The stubborn persistence of inches and feet in a world of centimeters is a powerful lesson in human psychology. We do not just use these old units, we inhabit them. An inch feels tangible because your mind has spent a lifetime building a library of what an inch looks like, from the size of a thumbnail to the gap in a spark plug. A centimeter, by contrast, can remain an abstract number on a ruler, lacking that deep reservoir of sensory experience. This is more than simple familiarity. It is a form of embodied knowledge, a language of the hands and eyes that is incredibly difficult to unlearn. The cost of forcing that change is not just financial, it is cognitive, asking an entire population to perform a constant, exhausting mental translation in their daily lives. This resistance is often framed as a matter of identity. For many, clinging to the imperial system is a quiet declaration of cultural independence, a way of saying our way of doing things has value too. It is a heritage written in miles per hour and ounces in a recipe, a familiar rhythm that feels uniquely their own. The practical barriers are just as immense. Retooling a nation's entire industrial base is a task of staggering complexity and expense. Every lathe in a factory, every blueprint for a skyscraper, every speed limit sign on 1,000,000 miles of road would need to be changed. For industries like American construction, where every 2x4 and every pipe thread is specified in inches, the switch would be a catastrophic disruption for a benefit that seems, from their perspective, purely theoretical. The result is the world we live in now, a patchwork of compromise. Scientists use nanometers while carpenters use 1/16 of an inch. Your soda bottle is labeled with both liters and fluid ounces, a silent truce in a century-long war between reason and habit. This ongoing standoff reveals a profound truth about technological progress. The best system does not always win. Victory often goes to the system that is most deeply woven into the fabric of daily life, proving that human tradition can be a force as powerful as pure logic. A digital architect designs a bridge not with a ruler but with pixels and pure logic. Inside a computer-aided design program, the fundamental units of measurement are the pixel and the bit, a realm completely divorced from the physical standards of the past. Here, precision is no longer about the length of a king's arm or the weight of barley, but about resolution, the density of pixels per inch, and data integrity, protected by complex error-correcting codes. This is a new metaphysics of measurement, built entirely on the principles of information theory. When a computer renders a complex three-dimensional model, it performs millions of calculations using floating-point arithmetic. This system allows for an incredible range of numbers, but it has its own inherent and often hidden imprecision. Tiny rounding errors can accumulate in these calculations, a form of digital friction that engineers and graphic artists must constantly anticipate and manage to prevent a virtual component from failing or a rendered image from displaying visual artifacts. This is the paradox of the digital world, a place of seemingly infinite precision that is nevertheless haunted by its own unique forms of uncertainty. Even our most precise hybrid systems navigate this divide. The global positioning system relies on the flawless timing of atomic clocks in satellites, a standard of temporal perfection, to triangulate your location on the physical Earth. Yet that position is almost always displayed to you in the familiar human-scale language of feet or meters, a necessary translation from the quantum to the practical. Digital fabrication has become the ultimate bridge between these two realities. A three-dimensional printer reads a file measured in abstract virtual units and translates it, layer by meticulous layer, into a physical object whose dimensions must be perfect in millimeters or inches. The slightest error in that translation, a single misread bit, can result in a component that simply does not fit. This new era has also created an entirely new category of things to measure. We no longer just measure land or cloth. We measure storage capacity in terabytes and the speed of our connections in megabits per second. Data itself has become a unit of measurement. The lost systems of the physical world have no direct analog here. The cubit and the shekel are meaningless in a universe of logic gates and electrical potentials. The digital realm has generated its own native metrology, one built from mathematics and electricity. This forces us to ask a profound question. How will our very definition of precision evolve as we spend more of our lives inside digitally constructed environments? The next frontier may not be measuring physical space at all, but quantifying the fidelity and immersive quality of virtual experiences themselves. Etched onto the golden plaques riding silently through the void, our message to the stars begins not with a greeting, but with a ruler. The diagrams on the Pioneer and Voyager spacecraft include a small, elegant map that defines a universal unit of length using the hyperfine transition of a hydrogen atom. This is the fundamental pitch of the cosmos, a wavelength any technologically advanced species should recognize, because hydrogen is the most common element in the universe. We cannot send them a meter stick, a fragment of a king's arm, or a weight of barley. To communicate across such unimaginable divides, we must use a language of pure constants, a system of measurement completely independent of our planet, our biology, or our brief history. This thought experiment forces the ultimate refinement of precision, a standard not for all humanity but for all intelligence. The hydrogen line, a specific radio emission, becomes a leading candidate for this cosmic standard. It represents a profound insight, the culmination of our entire metrological journey. The most advanced and trustworthy systems are not those carved in stone or cast in metal, but those derived directly from the immutable laws of physics. Designing such a system pushes the limits of our own understanding, forcing us to think beyond our terrestrial context. In a way, the creation of the metric system was a primitive first step on this path, an attempt to create an Earth standard based on our planet's dimensions. The dream of a truly universal metric is the final abstraction, severing measurement from any local context whatsoever. What would such a system tell an alien civilization about us? It would signal that we have learned the central lesson of our own long history. We have finally understood that the most perfect precision was never ours to invent, only to discover, written into the fabric of reality itself since the beginning of time. A laser scanner sweeps silently across the weathered stones of a Roman aqueduct, capturing millions of data points to create a perfect digital ghost. Yet the scientists are not interested in its length in meters. They are searching for a different number entirely, the precise length of the Roman foot its builders used over 2,000 years ago. This is the new frontier of metrology, where cutting-edge technology is aimed backward in time, reverse engineering the lost standards of the ancients. By statistically analyzing thousands of artifacts, from stone weights to the dimensions of temples, researchers can now deduce the master cubit or foot with astonishing confidence. The results are upending old assumptions. Studies of the Roman pes reveal it was maintained across the vast empire with a variation of less than half of 1%. This was not a haphazard approximation. It was a mass-produced, bureaucratically enforced precision that speaks to a quality control system rivaling modern manufacturing. This research peels back the layers of time to show us the true sophistication of ancient workshops and the reach of imperial administration. A standard that consistent enabled a prefabricated wooden fort to be built by a tired legion in a matter of hours, or allowed a water channel to maintain its gentle, life-giving gradient for 50 miles. Sometimes these recovered systems reveal solutions of elegant simplicity. The Roman pace, 5 Roman feet, was a brilliantly straightforward tool for a marching army to measure vast distances across unknown terrain without any equipment at all. Each rediscovery challenges the comfortable narrative of linear progress. It forces us to see that precision is not a modern invention, but a human pursuit that has been achieved in different ways with different tools across the centuries. By studying these lost metrics, we are not merely cataloging curiosities. We are expanding our own toolkit of ideas, learning that a clever solution to the problem of measurement might be waiting in the silent geometry of a forgotten ruin. What other forms of embedded intelligence might we uncover now that we have finally learned how to look for them? That quest for an objective standard forces a deeper question, one that has been quietly guiding this entire journey. What is true precision, really? Is it an absolute property of the universe, waiting to be discovered? Or is it a powerful idea that we ourselves impose upon a messy and complex reality? Our long march from the pharaoh's arm to the quantum vibration of an atom suggests a profound belief in the former, a conviction that the cosmos operates on a bedrock of mathematical order that we can, with enough ingenuity, finally quantify. This is the powerful allure of the modern sea system, a framework built from universal constants that would presumably hold true anywhere in the universe, completely independent of human observers. Yet, philosophers of science offer a crucial correction to this triumphant narrative. They remind us that every act of measurement is, at its heart, a form of modeling. We are not capturing reality raw, we are filtering it, simplifying an infinitely intricate world into a set of numbers we can manage. The very decision of what to measure and how to define the unit for that measurement is never a neutral act. It is a choice, and that choice is loaded with our own values, priorities, and the specific problems we are trying to solve. Consider the stark contrast in worldviews. The ancient cubit and the fathom placed humanity squarely at the center of the measurable universe. The world was understood through the scale of the human body, its labors, and its immediate environment. Precision meant creating a system that worked for building a temple or selling cloth in a local market. The modern meter, defined by the speed of light, tells a very different story. It reflects a cosmos of staggering scale, where humanity is a tiny, humble observer trying to decipher laws that operate with complete indifference to our existence. This shift from an anthropocentric to a cosmic frame of reference is one of the most profound intellectual transitions in our entire history. So perhaps true precision is not an endless, asymptotic race toward zero error. Perhaps it is the more pragmatic goal of creating a system that is perfectly fit for its purpose. The Great Pyramid is a monument to this idea. Its builders achieved a level of precision that was more than sufficient for their goal, creating a structure that has endured for millennia. Their system was precise enough. This suggests that the lost systems we have left behind were not primitive failures, but brilliant, context-specific solutions. They contained a deep, embedded wisdom about the human relationship with the world, a wisdom we risk forgetting in our pursuit of perfect, abstract universality. The history of measurement, then, is far more than a technical chronicle. It is the intimate story of our evolving conversation with reality itself, a record of how we have tried, again and again, to capture the fluid, chaotic beauty of the world in the clean, sharp lines of numbers.